Welcome to my video on the sine function for right triangles. So first let's look at what is a right triangle. I'll draw one right here. A right triangle has one angle that's 90 degrees. So that's going to be the one angle, that's going to be our right angle. Now we start labeling these other angles. This is going to be our angle theta. When we're interested in, that's opposite of this side right here called the opposite. And we're going to label that as B. And this is the hypotenuse. We'll label that as C. And this is called the adjacent side. We'll call that label A. Because this is adjacent, this length right here is adjacent to theta. The hypotenuse is always the long one. And the opposite is opposite the angle of theta, or the angle of interest. So that's defining our triangle. Now we define the sine function. Sine of angle theta is going to be the ratio of the opposite or the hypotenuse. Or that's just going to be, in the way we've written this, B over C. So the sine function is just a ratio. Now if we take the case for a right triangle, so these are going to be acute angles for theta. In other words, theta is going to be greater than 0 and less than 90 degrees. That's what an acute angle is. It's anywhere between 0 and 90. So if we think about this, like let's take kind of limiting cases here. Let's take the case where theta is real small. So there's our theta, and this is going to be our opposite, and there's our hypotenuse. So in this case, B is going to be small and C is large. So that's going to make this kind of a small number. And so the sine of this small number kind of goes to 0. Now let's take the other case where, let's draw our triangle here where we've got a big angle theta. So there's our angle theta. This is going to be our B, and there's our hypotenuse, there's our right angle. There's a right angle on that one. So in this case, that's going to be the B. So in this case, we've got B over C, and they're pretty close to equal. So B is kind of equal to C, or very close to it, because as this angle gets very large, they become virtually equal. So this is going to be approximately 1. So the sine of theta now is going to be approximately 1. And that's for angles approximating 90 degrees. So our sine theta is going to go from 0 to 1. Depending on the angle. So that's kind of our basic definition of the sine of theta. Now let's do kind of a real-world example here. This is a triangle. And one thing we have to do, though, before we get too far into this is we have to verify that this is a right triangle. In other words, that's got to be a 90-degree angle. So let's put it on our little compass, our protractor. And so that is 90 degrees. So we know that's a right angle, or very close to it. So what let's do next is let's measure some of these distances and verify that this sine relation really works for an actual right triangle. Now I'm going to measure these distances. We'll use a millimeter scale. That looks like that's about, we're going to say 95. So the hypotenuse, C, is 95 millimeters. Now the opposite, B, which is this one over here, let's see what that comes out to be. That's about 50 millimeters. So that's 50 millimeters. We're going to call this our angle theta. And then this is going to be our adjacent side. So let's see what that measures out to be. That measures out to be right at about 80 millimeters. Okay, so now in our definition, let's just verify this definition works. Oh, we need to measure our angle. because we want to verify that this is the same angle, what this angle really is. Okay, getting my protractor here. It looks like I'm calling that about 32 to 33. Let me get a little better. I'm going to call it 32 degrees. So theta is measured at 32 degrees. So now we know the sine of 32 degrees is equal to B over C. So B over C. B in this case is 50 millimeters. And C is 95 millimeters. Now those units cancel out, so it's going to be a unitless number. So now let's get on our calculator and really verify that. Get our TI-84. Let me turn it on here. Now what I'm going to do is I'm going to take the sine of 32, and I've got it in the degree mode. That's going to be equal to 0.592. Now, whoops, I didn't want to do that. Clear it. Now let's take the ratio of 50 divided by 95, and that's equal to 0.526. So those are approximately equal. So what that basically tells us is that this relationship holds for this right triangle. We got the sine of 32 is the ratio of 50 over 95 millimeters. And we plugged it into our calculator and calculated the sine, and that turned out to be the correct number. So we learned a little bit about the sine function for right triangles, the definition, and we did an example. Hope you got something out of this, and thank you for watching.